So we got some of that homework, quite a bit of it that's due, that extra problem 344 that I put out, 351, 353, 361, 362, 371 and 2. So I just thought I'd start in on it today, going over it a bit. So y'all doing okay with the sharing moment problem? Do we have any questions on that? So we got something like that. I handed this one out, And then we've got the dimensions. It's 2 meters near the shot there. So I think we got something like, is it about 4,000 over here? And I think that would leave about 16,000 here, I think. Is that right? $4,000 by 7, 28,000. I think I busted something there. This is 12,000, right? Yeah, okay, there we go. Something like that. All right, now I always like to get those kind of resolved. That's 2,000 by 2, so that's 4,000 there coming down. Okay. So what I'm seeing there is something like this. For the shear. I think that looks about right, huh? You're going to want to find these areas. Y'all okay with that? And then it's starting to look like something like this. Does it look about right for the moment diagram? Something like that. Now, the one thing that I want to emphasize on this is that's positive. That's a positive moment. So what that does is that makes the moment diagram go negative. Because what's happening here is you're kind of coming along on the beam, as you work your way across. and then you have this couple in there like that. So the beam reacts like that, see? The beam reaction is what you're tracking, so it's negative. So that's why that goes down, okay? So what's going to happen there is this is going to be a minus 20,000. Now, that's the change in moment. Okay. So that would be the approach on that one. Do you have any questions on that? There we go. All right. So that's that one there. Okay, so that's the last of the moment diagram problems. From there, we get into the tensile stress problems. Bending stress, I guess you call it flexure, 353 and 351. All right, let's have a look at 351 and 3 then. Those are the bending stress problems. Let's have a look at that. We look at 353 a little bit. They're fairly similar problems, these two. All right, so what you got on these, do we got any questions on this, on 351 or 3? All right, now there's a formula that we use, and the formula looks like that. So to get this thing figured out, you got to find M, C, and I. Okay, this is from the moment diagram. This is from the centroid. Which basically is the neutral axis. And this is from calculating I about the neutral axis. So that's the what you're doing with that. Okay. All right, so you want to generate a moment diagram. So you're going to generate those three things and pop them into the formula. That's what you're going to do. Okay. So I use the formula as kind of like a template that tells me what to solve for, is what I do. All right, now the first thing I want to do is get a moment diagram. So I want to find the reactions. I get 6,000 at A, 22,000 at C. I ran a little check there and it all checked out, so you know that looked pretty good. So 6,000 at A and 22,000 at C. So I start with that. Now I'm going to build a shear diagram, and then I'll use the shear diagram to get to the moment diagram. So that's the steps. So I've got those different reactions there at A and C, And from that, I just want to build a shear diagram. This just kind of looks like it's going to be a series of just rectangular blocks is what it looks like it will be. Okay. All right, so I'll get the 6,000 reaction will take me up from 0 for the shear to 6,000. Nothing changes. Then I've got 20,000. That will take me down to negative 14,000. Nothing changes. Then I'll push back up to 8,000. Okay, so I'm going up 22,000. Nothing changes till I get over here, and then I come back down. Okay. So that's the shear diagram. Now what I want to do, I want to get the area under the blocks of the shear diagram. Because whenever I see areas, I want to calculate them when I'm doing this process. So I get 6,000 by 3, that's 18,000. Negative 14,000 by 3 is negative 42,000. And 8,000 by 3 is 24,000. So based on that, then I can come up with a moment diagram. And what happens is I go from 0 and I change by the 18,000. I've got a slope of 6,000 constant there, so it's a straight line. That gets me from 0 to 18,000. Then I start at 18,000 and drop by 42,000. I end up at negative 24,000. So the slope in there equals the value of the shear diagram, so that's negative 14,000 in there. That's the slope. Now so the slope of the moment is the value of the shear. Shear doesn't change value in there, so that means I get a straight line for the moment, okay, because there's no change in slope. And then the last bit there, I'm at negative 24,000 because I went 18,000 minus 42,000. So I end up at negative 24,000. And then my last block there has an area of 24,000, so that gets me back up to 0. So that's a good thing because these diagrams should always close off to 0. And if they don't, you probably got some sort of error on reactions or areas or something like that, okay? So now I've got that moment diagram. And what's happening with this beam, if you look at it, this beam type is called an overhang. And what that's doing, on account of that first load, it's bowing down, but then it's got a load on the end that'll bow it. Well, here it's bowing concave down, or excuse me, concave up, and then it bows concave down. That's what's going on there, okay? So that does introduce a little bit of a little extra work, or whatever you want to call it, to be done here, because we've got a positive moment value there, but then we go to a negative moment value as the beam bends down. So the moment shifts from positive to negative on that beam, okay? Now I get pound feet out of that, but I want to convert to pound inches because my beam dimensions are inches. So I want to get into that unit system. So we good with the moment diagram? So what I've got here is I got the maximum moment, but I got two of them. I got one that's positive, which is at B, and then I got the other one that's negative at C, basically. Okay? So next thing I want to do there is find C, which is based on the centroid. Now, the other thing I'll mention here, I've got it labeled here, so I'll mention it. Notice what happens when you go from that positive to negative moment. When you've got a positive moment, compression is on the top, tension's on the bottom. But when you're in a negative moment, it flips. Okay? It has to do with which, on your curve, which is the inner radius and which is the outer radius. See, the inner radius is the shorter one, that's the compression. That's on the top for that first section there of that bowing. Right there. But on the next one, the inner radius is on the bottom, so that's where the compression is. The outer radius is the tension, it's on the top. Okay, so it flips, and you got to pay attention to that. So we got any questions on that? Okay. All right, then I want to figure out the beam properties. Okay, I want to figure out where the centroid is. and that's going to be the area of the top flange, which is 7 and 2 makes 9 by 2. It's 18 on the top. The Y bar distance is 6 plus half of 2. It's 7 up. And then the lower stem there is 2 by 6, which is 12. Half of 6 is 3. That's how far up it is. So I get 18 times 7 is 126. 12 times 3 is 36. Add them up, I get 162. Total area is 30. Divided out, I get 5.4 inches to the centroid of that beam shape, which is the neutral axis. So the neutral axis is 5.4 inches up. So what that's going to do, that's going to get me these values of C that I want, because C is the distance from the neutral axis to the edge of the beam. So that one's 5.4, that one's 2.6. Total is 8, so 8 minus 5.4 gets me the 2.6. So we're good with that? Okay. All right, so now I just go ahead and do the moment of inertia for the beam about the neutral axis. I go BH cubed over 12. There we are, we got 6, we got 36. We got the areas, we got the distances from the neutral axis to the centroid of each of those shapes, the flange on the top and the stem on the bottom. And you just take the area times the distance squared and get the AD squared term and add it to your BH cubed over 12. So 5208 for the first one and 105.12 for the second. Add them up, you get 157.2 inches to the 4. That's the moment of inertia of the T-beam. Doing all right with that? Okay. So now what we've got the moment, which we found earlier, right there. 2 of them actually, one at B, the other one at C. And then we've got the 2 C values up and down to the top and bottom of the beam from the neutral axis, and then you got I. So you just combine them. Now, there's a few things going on here. The moments vary depending on which point you're at. At B, it's 216,000, and at C, it's 288,000. Then the C values vary depending on where you are. At B, you're going up for compression and down for tension. Or excuse me, yeah, okay, so that's what you're doing there. Whereas at C, it's the other way around. You're going up for tension, down for compression. The up distance is 2.6. The down distance is 5.4. Okay? So we have to be a little careful here, when we calculate this, just to be sure we're getting the right stuff in there. What I've got is the value for the moment at B and then at C. 216 and 288, then I multiply that by the appropriate C value, then I divide it by I. Now I doesn't change, it's the same thing every time, 157.2. But the other things do change, and what they are depends on first where I am on the beam. At B it's 216,000, and then if I'm at C it's 288. But then I also have to account for the C value. At B, the tension is down, the compression is up. At C, it's the other way around. The tension is up, the compression is down. So I just got to plug all that stuff in, and rather than kind of thinking it through beforehand, I just ran all the numbers, and there's my biggest tension right there. It's 7420, and there's my biggest compression, 9893. Got any questions on that?
So in terms of finding C,
yeah.
What does that look like cross section?
Right there, a little crowded, but why don't we draw it up? So what we got, to draw up C is we've got this T-beam. And what we know about the T-beam is it's 8 inches deep. And we also know that the neutral axis is right there. It's 5.4 inches from the bottom. So that means it's 2.6 inches to the top. 8 minus the 5.4 gets you to 2.6. So what that means then is we've got C to the top, I guess you could call it, is 2.6 inches. And then C to the bottom is 5.4 inches. So you just kind of pick the way you want to go with it.
How do you know what C you're supposed to use in the equations?
Okay, the way you know which C to use on the equations depends on the moment diagram. Okay, and what's happening with the moment diagram on this is it flips, basically, because you've got an overhanging beam. So the moment diagram is right there, and let's just kind of clean it up a little bit. So what's happening with that configuration with the two supports on the beam is the beam bows down here, then it kind of curves, and then it, I don't want to, I guess it bows up. I guess, this other side comes down. So we're concave up here. And then on the other side, we're concave down. So it flips like that because of the loading configuration. So right in there, the compression's on the top and the tension's on the bottom because it's bowing down. If you take a section out of the beam at point B, what the section would look like would be like that. So this side's getting shorter and this side's getting longer, okay? But it turns around the other way at C. It starts kind of bending down towards D. So at D, a section of the beam would look like that. It's the other way around. So you got to check all the possibilities there. Now, as it turns out, what governs, there's quite an imbalance with this beam between C up and C down. The C down is so much bigger that it's the one that really determines which where your maximums are at. But rather than doing all that thinking, which makes my head hurt, I just calculate all the numbers and pick the big ones is what I did, okay? So that's how I approached it, okay? So what's going on there when I run the numbers is right here. See, I just run every possible combination. I put in the two different moments for B. So this line here is for B. And the line below is for C. So that's where the moments come from. So it's 216,000 at B, 288,000 at C. Then I put in my C up and my C down and track which one is which at those different points. Down is the tension at B, and up is compression. It's the other way around at C. Okay? So up is the tension at C, down is the compression. So I just run the numbers, pick out the biggest tension and the biggest compression. Those are the ones I'm going to design for. Okay? Good with that? All right. Good. Okay. Yeah, I just, it's rather than thinking about this too much, I just plug the numbers in, and that was how I approached it, All right. Okay, so that's a bending stress problem. And the way I think about this, again, I look at the formula and I just try and fill in the variables for the formula. There's three of them. M, which is off the moment diagram, C is off of the centroidal location, and I is just a moment of inertia for the whole beam calculated about the neutral axis. And plug them in. Find all those things separately and plug them in. Okay. Okay, now 351, this one's very similar, except it's not quite as complicated. It's just a simple beam that bows down. Oh, it's also just a rectangular beam, so that makes the C's equal everywhere, but, well, but on this one, what you're going to do is, here's your neutral axis. You're going to find, what we're doing on this one is using actually sigma is my over I, because we're asking what's the stress at these different points. So you just got to find the different y values. y1, y2, it's y4, here's y3, y5, okay? So you're just plugging in the different values there into the formula. Y1 is actually C top, and Y5 is actually C at the bottom, okay? But C means the maximum possible offset. It's like Y max. Y is a more general term. It means to any point you care to look at. Now, when you're doing design, you always use C, because that's going to get you the biggest stress to calculate for. But if you just done this problem, we're just looking at what's the stress in these different locations, 1, 2, 3, 4, and 5. So you just plug in the different Y's. So on this one, you're going to have one moment and one I, and then it's just a matter of plugging in the different C's and figuring out the stresses. Okay. So I just went ahead and did it like that, and just plugged them all in, got the different values. Okay. So we got any questions on that one? 351, similar deal. Okay. All right. Now the next two, 361 and 2, are shear problems. What we got going on there is a different formula. So tau is VQ over IT. To get V, you go to the shear diagram. Q is that AD. I handed that thing out to describe what A and D are. I is the moment of inertia about the neutral axis. And T is the thickness. So that's the 4 things that you're looking at for, and then you'll plug them in. Okay. All right. So on this one here, what I'm doing, I'm just creating this chart that allows you to calculate Q for the different locations. So what we're doing here, we're finding the shear at points 1, 2, 3, 4, and 5. And it's at point B there, which is 2 meters from A. So B is 2 meters from A. And then we're going to, at B, we're going to investigate points 1 through 5. Okay. So what you want to do there is go ahead and solve for these different values. Okay, I went ahead and found the shear diagram, which looks as shown over there on the left. So that goes from 0 up to 2,800, and then it comes down in a linear fashion down to negative 400 because of that area. Negative 3,200 there for the area. There we go. And then it drops, okay, by the 1,200 load. So then we're down to negative 1600. Then it drops from there down to negative 3200. And then that reaction brings it back, okay, to 0. And so the reaction brings it back to 0. All right, so what we want to do, we want to find the shear at B1, 2, 3, 4, and 5. Now the shear, the V value is right there. You got a linear slope there with a slope of 800 negative. So if you take the value of shear on the right, which is 2800, and then go minus the slope, 800, times the offset distance, which is 2, you'll come up with the shear there. It's 1200. So that's the shear at B. Okay. The thickness of the beam is just, the thickness of the cross section. It's 4 centimeters, so that's 0.04 meters. I is just BH cubed over 12 because it's just a simple rectangle. So it's 1.71 times 10 to the minus 6. So to find the shear at these points, we got V, T, I, and we need to find Q. Right? That's the last thing we need. All right, now what Q is called the first moment of area. It's the area that would shear off if the beam failed at a given point. And then to that, you multiply that by the distance from the neutral axis to the centroid of the area that would shear off. Okay. So there's a run through some of the Q's there. At point 1, there isn't any area that would shear off, so the area is 0. The distance is 4 centimeters, 0.04, so Q up there is 0. At point 2, if the failure occurred there, what would shear off would be 2 by 4 centimeters, 0.0008 meters squared. And then that distance to the centroid would be the 0.02 from the neutral axis to the base of that rectangle, plus half a 0.02 more, so that would be 0.03. That's the distance from the neutral axis to the centroid of that rectangle. All right, if it shears at the neutral axis there, the area would be 4 by 4 centimeters, 0.0016, and the distance would be half of 0.04, it'd be 0.02. So 0.0016 times 0.02 gets you 32 times 10 to the minus 6. So there's some of the different Q values that you could generate for those different locations. In each case, they're the area that would shear off if it failed at that location, and then you multiply that by the distance from the neutral axis to the centroid of that area. Okay. Got any questions on that? So we got V, Q, I, and T now. V from the shear diagram. I is just BH cubed over 12 because it's a rectangular beam. T is just the thickness of the beam, 4 centimeters. And now we found Q for these different locations. There's 2 more to find, though there is a lot of symmetry on this one. I'll mention that. Okay. So you just plug in everything. So there's tau for B1, B2, and B3. You'll notice that that shear maximizes there at the neutral axis. That's where it's maximum at. It's down the center of the beam. Okay. If you want to find tau max for the beam, you take 3 times V max over 2 times the total area for the beam. It's basically 3/2 times the average shear. It's 1,500,000. Okay. So I asked a couple questions there to find the shear at B1, B2, B3, B4, and B5. So you still got to do B4 and 5. There's a lot of symmetry in this problem, though. And then the maximum shear is 3V over 2A. So we all right with that one? Good. Okay. So that's the shear and beams, okay? .363 is very, very similar. It's a very similar type problem, except you just got one shear to find, that's all. Okay, two more shear problems. One is shear flow, the other one's shear center. This one here, we've got this I-beam that we've built. We want to find the shear flow for this because we're interested in the force that will build up in those screws. They're set up at 6 centimeter distances. So to do that, we want to find the shear flow, which is F, which is VQ over I. So I, on this one, it's a symmetrical beam, so I just take the base times the height cubed over 12 minus 2 times those cutouts, which would be their base times their height cubed over 12. Comes out to be 0.0000936 meters to the 4. So that's the I value for that beam. Now remember, you can't do that with T-beams, you can't do that with L-beams, it doesn't work, but you can do it with an I-beam. You can get V easy enough because of the shear diagram. Just pull the V off the shear diagram, looks like 2,000. And then for Q, you want to look at the area that would shear off. 8, 8, and 8 makes 24 times 3 centimeters. In meters, that's 0.0072. Then you look at the distance from the neutral axis, which will be in the middle of that web, to the centroid of the area that would shear off, which is that top board. So that's half of 12 is 6, plus half of 3 is 1.5. So 12 over 2 plus 3 over 2 gets you 7.5 centimeters. So you take the area in square meters times the distance in meters, and you come up with Q, 0.00054 cubic meters. That's what we call Q, and that's the value for that top board. Okay. So we're on this thing here, and we're looking at its tendency to shear off. See, when that beam gets loaded, everything's going to flex down a little bit, but that board's going to want to flex more than that big solid web underneath it, I think. They're going to have different radii of curvature. And when that happens, they're going to start doing that, or they want to. But those nails, or whatever they are, nails, screws in there, and they're going to hold it together. They're not going to allow that sliding to happen, okay? So they're going to get shears that build up in them. They're going to try and fail along that sliding plane. We're finding out how much force builds up in them, because we got to be sure they can handle it. See? That's why we're doing this, okay? So what you got there when you run everything together is you're going to get what they call the shear flow, which is a force per unit length. It's 11,540 newtons per meter. Now, if you space those bolts at 6 centimeters, you multiply that by 0.06 meters, you get 692 newtons in each screw. The units come out. So, not quite sure what that is. Maybe 150 pounds, something like that. I'm not sure. So each screw has to be able to handle that. That's the force that'll get built up because of that sliding action. Yeah, a little bit more than 150 pounds, I think. Okay. So again, I just let the formula tell me what to do. I need V off the shear diagram. I need I for that beam cross-section about its neutral axis, and I need Q, which is that first moment of area. Just be sure that you know what this one is, okay? On the formula sheet, you're given the formula for it, but that, sometimes people need a little bit more information than that. A is the area that would shear off. If it failed. And then D is the distance from the neutral axis to the centroid of the area that would shear off. So just be sure you kind of get that figured out, because again, I'll have these on the final. And what you're going to have in your formula sheet there is AD, so you want to be sure that you know that, okay? And I'm kind of warning you, because after grading however many years of finals, it seems to be a thing where people trip up a little bit. So just, just be sure you got that one figured out, okay? So we good with that one? Good? All right. So that's shear flow. So if you're building stuff and using connectors, you're getting those shear forces building up in them. And this is how you see what that force is going to be, so you can make the connectors strong enough to hold the thing together, okay? All right. One more, the shear center. Got a C channel there. We want to figure out how far to offset this load. All right, now this stuff is a little, I don't know, it's a little complex. I don't know what the right word is for it, but this isn't just doing arithmetic or something or plugging into a formula. It's a little bit more to it. Okay, so I sketch in what the shear is going to do. It actually does kind of flow through the object. Okay, you pick the centroids. Your reference points are kind of the centers of the different pieces of the C channel. So this point would be an inch in from both sides, edges. There's a point down there. What I'm going to do, I'm going to take moments about that point, because that will eliminate two of the shear flows that I have to deal with. So I'm doing that on purpose. And I'm putting that in the middle of the top flange and the middle of the web. That's the reference point, okay? So if you take moments about that point, and I don't know if I gave it a name or not, I called it point A. So point A there, that's going to be purposely put in that center of the web and the flange there. The intent there is we're going to take a moment about A, and I'll eliminate two of those forces, two of the three forces from that equation by using point A, okay? I'm doing that with intent, okay? All right, now I'm going to have to calculate a shear flow, and what I'm going to do here, I'm going to sum a shear flow going through that lower flange, because I got the upper flange and the web eliminated, so I'm going to find the shear flow in the lower flange. That's VQ over I. Now I want to find I about the neutral axis, and that's a symmetrical beam. It's a C channel, so I can do that. I can go the base times the height cubed over 12 and subtract off the cutout, the 6 by 8 cubed over 12. Now I can do that because it's a C channel and it's symmetrical about the neutral axis. What are the two beam shapes that doesn't work with? L? Okay. All right. But don't work with those, okay? So again, why am I mentioning this so often? This might come up. Don't try and do that with a T or an L, all right? It ain't gonna work. It just didn't, okay? Okay. All right, now, what I wanna do now is I wanna get that formula going, the F equals VQ over I, all right? Now the V is just off the shear diagram. V is just gonna be whatever it is, because it kind of affects all the terms in the equation. You don't know what V is. This would work for any loading on that beam is kind of the idea, okay? So V is just a letter, and it's not significant. Don't worry about that. Okay, I, we found it's 896. Now we got to find Q, all right? Now what we're going to do here is we're going to start at the edge of that flange and work our way across it. And we're going to sum this shear flow as our goal here to get the total shear force in that flange. Okay, so I'm going to come over a distance x. Now the area there is going to be 2 times whatever x is. See that area of that thing, if I pull it up where I got some space right there, if I work my way across, this is 2, and I'm working my way across at x, so the area is 2 times whatever x is. Okay, I'm generating a formula that I'm going to integrate is what I'm doing here. Okay. Now the distance, so that's what A is. So A is 2 times x. Now the distance is just the distance from the neutral axis down to the centroid. Now, see, the centroidal location doesn't matter what x is. The centroidal location is at the middle height of that flange. So there will be one distance there. And what that distance is half of 8, which is 4, plus half of 2, which is 1. So the distance is 5. Okay. So what I get there for Q is the area, which is 2x, times the distance, which is 5. That's 10x. Okay. So I'm going to take V times Q over I, and I get 0.01116 times whatever the shear is. And then times x. Now what I'm going to do then is I'm going to sum up that shear flow across the flange as I go. Now the flange is 6 inches plus 2 inches of web. And as near as I can tell, this is just an empirical, meaning just based on experience kind of assumption. You assume that the flange extends halfway into the web. So we're going to assume that that flange is 6 plus half of 2. It's 7 inches. We're kind of taking this area, which is kind of ambiguous. Half of, is split between the web and the flange. So I'm going to give half of it to the flange and half of it to the web. I think that's really about as deeply as that's thought out, okay? I don't think, I've not seen anything to indicate otherwise in the reading I've done on this, okay? So we just go from 0 to 7 with the integral. So it's 0 to 7.01116 Vx dx. The V is essentially a constant, so it comes out. And it looks like I'm kind of forgetting my V here, so I'm pulling the V out. I think that ought to be there. Because I pull it out of the integral, basically. And I'm left with, when I integrate 0.01116x, I get 0.00558x squared. And that goes from 0 to 7. Plug in the limits, and I get that 0.2734 times whatever V is the force that builds up in that flange. You might think of that as being 27.34% of the shear force ends up in the flange. All right. So now I know that. Now that's 10 inches away from my point A. What that's going to do is basically start, this is really a reactive shear, which is kind of weird, but I get a moment like that. And I'm going to, and really what's going on, if when you load this thing up, if you load it over its centroid, it's going to curl the other way. So you got to offset that shear load by an amount to counteract that moment. The moment is 0.2734 V, which is the shear force times the 10-inch offset. And so you take V times E. E is called the eccentricity. It's how far from A you'll offset the load. So whatever the load is, V times that eccentricity is the 2.734 times V. So the V's just cancel. You get how far to offset the load. 2.734 inches from A, which is 1.734 inches from the edge of the B. So if that's a truck, that's where you put the motor mounts is the idea. So the beam won't warp up, won't bend and twist. Okay. So there you go, a bit of homework there. Yeah, all right with that? Okay.